Oops.
But yeah, so I'm going to start with really ancient history because I find it funny. So the ancient, at least in Europe, the ancient Greeks were the first ones to start pondering what the nature of light is. And one of the first people to write about this extensively is Euclid, which is like 300 years BC. And he wrote that, so he observed that light travels along straight lines and concluded that what happens is our eyes send out like beams that probe stuff. That's, which was very easy to disprove because you're like, well, why don't we see in the dark? And then the Greeks went through a whole thing of trying to come up with really complicated ideas for why our eyes still send out beams, like probing things, but we can't see in the dark. So yeah, they came up with ideas that like there are sources of light which emit atoms. I have no idea what atoms are, but they emit some kind of particle. And what we do is we take the beams that go from our eyes and we push those atoms against some wall, and when those atoms, or against some object, when those atoms hit an object, that's how we see. It was really complicated, as the Greeks like to do. And then nothing, and so then the Roman Empire fell apart. All of this stuff was lost, at least to Western Europe. However, the Muslim Empire formed in what, like 900, 800 AD, and so in the year 1000 AD, this guy Hassan ibn al-Haytham. So he got a hold of all of these ancient, he was analyzing all these ancient Greek texts by Ptolemy, by Euclid, and he was a huge fan of this idea that he observed that light has to travel along straight lines. But then he also, so by this point in China, they had already invented the camera obscura. Do you guys know what the camera obscura is? Yes? Does anyone not know what the camera obscura is? Okay, so it's a pinhole camera. And the idea is very simple. So what you can do is you have some screen here. And so here you have a tiny hole. And here you have some tree, let's say. And I don't know. So the tree is illuminated. It has to be really, really bright. And in this case, so the only light that goes to hit this part, considering the box is completely dark, is the light that goes along this line, right? And the only part that goes to hit this spot is the light traveling along this line. The only part that hits this spot is light traveling along this line. Does that make sense? So, and then you end up seeing some tree upside down like this. And to flip in every orientation. We built one, if you guys want to check it out. We can do that later. But, so he looked at this thing and he thought, well, this is getting way too complicated. I can't justify the fact that if I'm sitting here seeing this image, what does it mean that my eyes are sending out rays which are somehow going off of this wall and then probing this thing? Then that seems way too complicated. So he's the first guy to figure out that it's actually light rays coming into our eyes, that our eyes aren't probing stuff. Yeah. And then he also, he had anatomical drawings, so from he read Hippocratic texts, and he had this Hippocrates who wrote the Hippocratic Oath, right, that all doctors take now. You guys know what I'm talking about. so they read his text, and they tried to figure out how the human eye worked, and he proposed that the human eye worked something like a camera obscura, because that's the only way he could imagine getting some sort of image. And then for the next, again, 600 years, nothing happens, and then, then the Crusades happen in, what, 12th century, roughly? And along with looting and pillaging, the Crusaders steal a bunch of the scholarly texts. And when the Renaissance hit, now European scholars are reading this stuff. And comes along Kepler. That was awful writing. So, do you guys know what he's famous for? He's a really famous astronomer. Did a ton of astronomical observations and stuff. But he worked with lenses. They had just invented the telescope at this point, and he worked with lenses, and he realized that the eye works like a lens, and So he realized that the eye works like a lens, and when he tracked the rays through the lens, he realized that the image would be upside down again, which was a big counter-argument. So the people didn't like this idea that the eye works like a lens, because then we would be seeing the world upside down, and that didn't make sense. They didn't figure out that the brain just is used to seeing everything upside down and flips an image. There's some funny experiments done with this, by the way. People were made to wear glasses that flip the image. So the image that's now printed on your retina is flipped twice, which means that you're seeing it the right side up, and you get really disoriented. And then after a few days of constantly wearing these glasses, your brain rewires itself, so you are again able to function, see everything. And then they take the glasses off, and they're again disoriented, because now they're seeing everything upside down again. So that was Kepler's contribution. And at this point, people started this is approaching the time of Newton, where modern physics is starting to be born. And the big question is, what is light anyway? So physicists knew two things. There are particles. We all know what those are. They're atoms. They fly in straight lines. They hit stuff. And then there are waves. And we also we all see waves on the ocean. They travel through some medium. So the big question was, is light a particle or is light a wave? And so the winning idea, the prevalent idea during that time is the only way you can explain why light travels in such straight lines is if you can say light is a particle. And so there's this guy Newton and Poisson. So this guy is 18th century. This guy is very early 19th century. They were very certain that light was a particle. But then it was really hard to explain phenomena like refraction. So there was a camp of guys who thought that this was a wave. And one of them was this guy, Huygens. Did Gleason say anything about Huygens? Okay. Well, Huygens in 1670s proposed that the way light propagates is we can treat every single point. So every single point you can treat as emitting light in a circle around it, right? Circular waves. And so, and together they make wavefronts that will propagate light. That was the idea. It wasn't a very well developed idea at that time because, yeah, so they didn't quite understand how interference worked yet. But this was Huygens, they're called Huygens wavelets. So, sorry, there's a G here. And remember this idea, it's rather important. So and so there are lots of texts written just based off of various observations. Nobody could really agree. And so what was really important, so now we get to the double slit experiment. So in comes Thomas Young. And in 1801, he had been studying how sound propagates. And in 1801, he publishes the double slit experiment. And so the idea is this. You have, let's do this. So let's imagine that we have two slits like this, and we have light coming in on this side, right? And here we have some sort of screen. So if we have particles coming in, how would this look? What pattern would you see on the screen?
We would only show it at two places?
Yeah.
Like where the slits are?
Exactly, yeah. So there would be some really bright, this is the axis of how bright it is. That's what particles would do. Now let's see what waves would do. So, actually I'm going to phrase it this way. He sent light in. Here we have our wave fronts going in this direction. And the pattern of brightness that he saw looked something like which didn't make sense with the particle picture at all. First of all, there's this big bright dot right in the middle of this guy, which doesn't make sense. And then, if opposite of these points, it wasn't necessarily a bright spot. So he proposed that this was an argument that light is waves. He didn't really figure out how this pattern is created, but he proposed that light is waves. So, oh yeah, we can show you what exactly he saw, because we have the double slit experiment set up here. So there is, the way this works is there's a laser and then it bounces off two mirrors and it goes through this thing which has a double slit in it. And then it'll shine on the wall. So, let's see. Can you guys kind of see the red thing? Yeah. So, yeah, let me. Oh, no, I don't know where the lights are. Sure. Let me try to do a different pattern. Oh, that's the wrong mirror. Okay. So, maybe this isn't the best pattern. So, yeah. Okay, you can kind of see it right here, right? So there is this big central bright spot right here, right? And then it gets dim, and then there are bright spot, bright spot, bright spot, and so on. It falls off like that. Yeah? So, and there's actually, if you look closer, there's a second pattern somewhere there. There we go. So there's a second pattern, which we can talk about why it's there later, but that's what he saw. And so this wasn't consistent with the particle theory. And this was a kind of a big shock. And so the French Academy of Sciences, which was run by, or one of the main people in it was Poisson at that time, who was a famous mathematician, invented tons of stuff. They said that they're going to publish a prize for whoever can explain this thing first. And they were very certain, they were so certain that light is obviously a particle, that there had to be some particle explanation. It bounces off the sides of the slit, something like that. So so it took them a while to actually get to this, but in 1817 they announced this prize, and in 1818 Fresnel explained what is known as the wave theory of light. And so the idea is this. So there are so he took two things. There is Huygens wavelets. And so he said, yeah, light spreads out from each point, but there's also interference. So has Gleason talked to you about constructive interference, destructive interference? Yeah? Okay. Basically, yeah, the simple point is particles kind of run into each other and hit each other. Waves waves add on to each other. So if we have a wave coming in like this, and you have a second wave also like this, right? So they're both in the same place at the same time. The result will be a wave that looks like this, right? So this is twice this. So this is constructive interference. On the other hand, if you have one wave like this and another wave like this, so these are, then you have destructive interference, and you don't get anything. So that's a property of waves. And so Fresnel decided that let's apply this to that. So I'm going to draw a picture that's going to try to explain how you get this pattern out of the two slits. And the picture looks something like this. Let's imagine the slits are infinitely, so yeah, first a bit of notation. This part I'm going to draw, because we're now going to look at this is one spatial dimension, right? So these are looking at one-dimensional waves, but now we need to look at waves in two dimensions because the blackboard is two-dimensional. That's great, but I don't get to draw the full shape of the wave. So what I'm going to draw of the wave is going to be, this part is going to be a solid line, and this part is going to be a dashed line, right? So if we have two solid lines intersect, that's constructive interference. If we have two dashed lines intersect, that's also constructive interference. If we have a solid line and a dashed line intersect, that means destructive interference, and you don't see anything there. Does that make sense? Not an agreement or not a disagreement.
You say it one more time?
Yeah. So I'm going to draw a picture, and I want to show these waves moving in a two-dimensional space. So I'm going to draw the crests of the tops of the waves, or what's going to happen is I'm going to freeze. So these waves are moving through our medium, and I'm going to imagine take a picture and freeze that moment in time. And I'm going to draw the tops of the waves as solid lines, and the very bottom of the wave as dashed lines. So what happens is if we have a solid line intersect a solid line, they add together and we see a bright spot. If we have a dashed line intersect a dashed line, they also add together and we also see a bright spot. However, then, if we have a solid line and a dashed line intersect, that means that they add together to nothing, so we don't see any light there. And so the way this works is we have light coming in from far away. So it's parallel lines. So we have, here's this part of the wave, then some while in there's this part of the wave, so on. And so this is light moving in this direction. And here we run into our slits. Maybe I should. And we imagine that the slits are infinitely thin. So, and then, so if they're infinitely thin, then they act like just one single point. So we have waves now spreading out in a circle after them. And then here we have solid line. Then we have, I'm going to try to draw this neatly so that dashed line. We have another solid line. Let's draw one more dashed line. Something like that. So you see we have constructive interference here, right? Constructive interference here, constructive interference here, and constructive interference here, if I drew that correctly. All right? So along this line, we have constructive interference, right? Then we have, so if we have some screen over here, we would see a bright spot right here, right? And then we have destructive interference, destructive interference, destructive interference. So here, we would not see anything. Then we have, again, constructive interference, constructive interference, constructive interference. So here we would see a bright spot, right? And same symmetric thing on that side. Does that make sense? So what it turns out is that at certain angles, you have bright spots, dark spots, something that looks like this. So now let's see if we can actually figure out the angles to these bright and dark spots. So we want to try to basically figure out this angle right here, right? And so the way that you do that is you say, okay, let's look at here's our, by the way, are there any questions at this point? Is it clear to everyone? Yeah. Okay, cool. So, and we need to take we need to imagine that this is infinitely far away compared to the width of these slits. So right now, if you guys, I don't know if you guys can even see, but when we did this experiment, you can actually see the two slits, but they're the ones right here. Right, so they're really close to each other. And we projected this light over this big of a distance, right? So what happens is if we had light coming in here, and we were looking at something like way past this wall, we wanted to track the two rays that come together somewhere really far away, right? Well, near here, they're basically going out parallel to each other. So we have these wavefronts. So let's look at what happens in this direction. Well, in this direction, there's some wave going along, right? Same in this direction, there's the same looking wave. So here's our solid wavefront, here's our, does that make sense? So I'm just gonna draw now these lines. So let's look at what happens along this direction. And so this beam is gonna intersect with this beam somewhere really far away. But since we're talking about this is so small compared to this distance, we can treat this angle as the same as this angle, right? Actually, we should be using this angle. Yeah? And so, well, let's look at how much further does this beam have to travel than this beam? Well, it has to travel this much further, right? So if this distance is lambda over 2, so the wavelength over 2, what's going to happen? Is it going to be a bright spot, dark spot? This picture.
Should be a dark spot.
Why?
Because one wave is going to be at a crest while another one's at a trough.
Yeah, exactly. If we draw this wave, so we have this wave coming out of here, and this is kind of small probably for you guys. Yeah? Okay. Now let's draw a more extreme case so it's bigger angles. So if we have this wave coming out of here and same wave coming out of here, well look, the crest lines up with the trough. This trough line will line up with the crest, so it will interfere destructively. If this is lambda over 2, right? However, if it's I'd have to draw an even more extreme picture. But if this is lambda, now you fit a whole wave in here. So now your crest will line up and your trough will line up, and it will be a bright spot. Now, yeah, so we also can get the next order if we fit 2 lambda in here, right? Then we have, it will again line up, and we'll get another dark spot if we fit 3/2 of a lambda. So does that make sense? So I think you guys will have to do this calculation on the homework. I'm pretty sure. So that's the end of the strict double slit experiment. Poisson, who was on the committee to judge all these submissions, looked at this and he really didn't like it. So he tried to find something wrong with it. And so let's So, and he proposed this, what seemed to be a ridiculous thing. So let's say we have light coming through and there's this metal disc here that's blocking the light, right? And we have light coming through right here, and we have some screen, right? Well, obviously, there's going to be light here, and there's going to be a shadow. But according to this, Fresnel's theory of light as a wave, this point right in the middle, it would be the same distance from all the edges, right? So it would be the same distance from all the edges, and therefore, the light, same number of wavelengths would fit in light coming from this edge and this edge. So you should see a tiny bright spot right here. But Poisson thought this was absolutely ridiculous. This obviously disproves his theory. And then this other guy named Arago who was also on the committee, he decided to do the experiment. And so we have the experiment right here. So we have this thing has the little metal disc, right? We're gonna send the laser beam through one mirror, second mirror, and then we're gonna use lenses to spread it out. So we have this even like beam of light coming that has actually a width unlike a laser beam. And hopefully, you guys might wanna come closer or because this is gonna be hard to see. It is really faint, but. Okay, so you guys see the ring on the wall? So if anyone wants to come closer and look, right in the middle there is an actual like little bright spot. Do you guys see it from there?
Yeah.
This thing right here.
Yeah.
Oh, cool.
Barely,
Yeah. So this experiment was done in like 1818 also, and absolutely seems to show that light is a wave. So this made Fresnel win the prize. And yeah, but this is called ergo spot or Poisson spot or Fresnel's bright spot. I don't know why Fresnel gets it right, probably because he's the one who won the prize. And so it would seem like that light is a wave and there's no other questions about it. And people thought that so there's some debate until like the 1860s still about whether light was a wave or a particle, but basically people did more calculations similar to this stuff, people did more experiments, and by the 1850s, 1860s, it was completely certain light is a wave, there's no other way of thinking about it. And this lasted until the early 1900s, basically. And so, so what I'm going to tell you now should be kind of disturbing, because I just proved to you beyond, like I showed you the experiments, light is obviously a wave, right? Do any of you guys have any doubt about it? So, this is something called the photoelectric effect. It's one of these like fundamental experiments that's considered foundational in physics. So there wasn't exactly one person who did the photoelectric effect experiment. It's actually a combination of many people who did experiments between like 1880s and 1910, basically. But eventually what they came up with is this. So what you do is you take a really bright light. Here's our flashlight. And you shine it on a piece of metal. Right? And so on this piece, the reason why you choose a piece of metal is because metals conduct. And that means that you have these electrons in the metal that are kind of free-flowing, do whatever they want, and are easy to rip off from the surface. By the way, the early 1900s is also when we discovered that the electron is a separate thing and figured out what to do with it. So, and if you shoot light that's strong enough, the idea is you get electrons that fly off. So the idea was this, that let's see what happens if we, let's see what happens. So if we have light intensity, so on this axis, and so this is number of photoelectrons, electrons that fly off that we measure here. Well, if light is a wave, then you keep adding intensity, so you keep growing the amplitude of the wave. That means more and more energy is deposited. So it should do this. However, what they saw was actually this. Either there were no photoelectrons coming out, or if they picked a different light, there were. So then they decided, okay, let's look at number of electrons as a function of frequency. And what they saw was really weird. So, like, there's nothing coming out at all, and then at a specific frequency, all of a sudden, there's stuff coming out. So this is higher frequencies, so more violet light, and that's it. So this was really weird. There was a lot of people working on trying to explain this. One of them was Albert Einstein. Do you guys know what Albert Einstein got his Nobel Prize for? For what?
For explaining.
Yeah, exactly, for explaining this. Then he invented relativity, and then he invented special relativity and general relativity, which is what he's actually known for. But because you can only get one Nobel Prize per subject, you could already taken it up on this. So there are actually two Nobel Prizes. The other guy is Millikan, who measured the charge of the electron using something called the Millikan oil drop experiment, which is an awful experiment. So he got a Nobel Prize for doing experiments to try to explain this stuff. Yeah, but the thing that Einstein came up with is you can't have any amplitude of light. You can only have very like fixed increments of amplitude. So basically, it's like a particle. The particle either has some amount of energy or not, and the amount of energy stored in the particle depends on the frequency. So the higher the frequency, the more energetic the particles are that are hitting you. So if you're right here, right, you can have as high of an intensity as you want, but you just have a lot of particles with very little energy. And then you keep going, and all of a sudden you cross this boundary where suddenly one single particle has enough energy to actually knock an electron off. And that's when you start seeing the electrons fly out. So this seems to definitively prove that light is a particle, but we already have all this stuff proving that light is a wave. So, and that's when people came up with something called wave-particle duality. And this is the foundation of quantum mechanics. By the way, so these particles of light are called photons. But this is really weird. So you have stuff that's kind of like a wave, but kind of like a particle. But then they started thinking, well, maybe other particles also do this. So let's try to do the double slit experiment with electrons. And it turns out, if you do the double slit experiment with electrons, you will also get the same pattern. So electrons are also waves. And then you can do it with any particle that you want. And it turns out that all particles sometimes behave as a wave and sometimes behave as a particle. So it's not that we have these two things, like sometimes waves, sometimes particles. In reality, everything behaves as this weird blend between waves and particles, and sometimes it's convenient to use one set of rules, sometimes it's convenient to use the other one. So, yeah, that's the end of the explanation. Do you guys have any questions? Thank you.